thank you very much for your presentation. Beatriz, you are there?
Yes, I'm here. I don't know if you can see me and hear me.
No, we can see and hear you very clearly. And
very good.
Thanks a lot. So the talk is open for discussion. So you can either raise your hand in order to ask your question in person, or you can post a question in the Q&A chat, so to say.
I think I'll start the discussion. So you made this analogy of your learning materials to the human brain. The human brain has a stage where it learns and then where it's sort of more static. Would you imagine something similar for your learning hardware, that sort of you have a condition where you can train it, but then also how would you realize a condition where it's then a bit more persistent, such that it doesn't forget immediately what you just taught it?
Yeah, so that's a very interesting question. We have an enormous variety within materials. We have materials that are intrinsically non-volatile, like ferroic systems, for example. And we have systems that have volatility. So there are also volatile memory stores that people are investigating. And we have systems that combine different types of functionalities with very different timescales. So you can utilize different physical phenomena within the same material to access short or long timescales. And this is a little bit the game that we need to play. You have long-term memories, short-term memory, all these are needed to learn. And we are very familiar with memories like ferromagnetic memories or ferroelectric memories, systems that have intrinsic non-volatility, but we are not so familiar with utilizing all the possibilities in between these intermediate time memories and the short-time memory. So there is a huge spectra of phenomena, for example, using defects in traps and releasing defects from traps with different time scales, using different levels of energies to access different time scales. Once you control the materials and you really have the control, very well control the material at the nanoscale, you can dream of using a very large range of possibilities.
That sounds very exciting. Are there further questions from the audience?
I have at least 5 more.
Well, then, Ralf, go ahead. We have one more question by Ralf Ernstdorfer. Ralf, you want to ask your question, please?
Thank you very much, Dr. Boldorf. You have an idea on the algorithms you need to sort of connect from the outside to your learning hardware? Because I mean, in the human brain, somehow we don't need an external algorithm. It's also kind of realized within this learning network. So yes. How do you imagine the kind of the software interface between a normal logic and a learning hardware logic?
Yeah, this is also a very interesting question. That's why you need this multidisciplinary expertise. You cannot approach this from the materials point of view. At the moment, we are getting inspired by the artificial neural networks, which in turn are inspired by the brain. But it may be that at the end, once we really have the devices that substitute transistors in this to create this plasticity at the hardware level, we may need a complete different algorithm philosophy to address them. And we need to think of the hardware, and the architecture also will be probably a complete different type of architecture in a computer like that, and therefore the algorithms will be also different. We hope that the levels, so the strength of von Neumann computers is the fact that all these levels in the computer are totally separated from each other. Is considered as a huge advantage that the software engineer doesn't have to know anything about transistors or about semiconductors. We are afraid that in a neuromorphic computer, this cannot happen, that really all these levels have to be integrated at a much more intrinsic level. And that is the difficulty. And that's why you need to actually educate a new generation of scientists that learn already from the beginning that you cannot totally separate the software from the hardware. And we think this will need a lot of time, that this is a long-term process, and that we need to educate ourselves in this direction.
Thank you. There's one more question in the Q&A chat. So if we use this type of transistors having short-term memory, will the data be erased over a period of time? Or I guess the question is, how do you connect it to a persistent memory device?
Yes, exactly. So it's a combination between a long-term and a short-term memory, and the fact that you co-localize those in the same material or in the same device, which is at the moment, at the end, we are doing this for the energy saving. We think there are orders of magnitude of possibilities of saving energy, and the co-localization of processing and memory is one of the key questions. So if you can have a material in which you have, of course, you need non-volatility. You should have a physical phenomena that allows you to store your memory long term. This is necessary, and that's totally should be there. But if that same material, for example, a ferromagnet that can give you this long-term memory at the same time has a set of defects at different levels in the band gap that you can release in a very controlled manner, then you can combine the long-term memory and the short-term memory. And you can forget things that you don't need anymore. And this type of dynamical memory processing is of course a key also for the energy savings in the brain and our ability to learn.
Mm-hmm. Thank you.
Okay. Yeah, then we probably proceed, or are there further questions? If so, last chance to raise your hand or to type something in the Q&A session, chat.
I don't see anything.
Okay.
Okay. Beatriz,
Thank you
very much.
Thank you for having me, and congratulations for this very nice conference. Bye-bye.
Thank you.